Hello everyone, my name is Thomas Ott. I am a research hydrologist at the Desert Research Institute, as well as a recent graduate from the Graduate Program of Hydrologic Sciences at UNR. Today I will be presenting my work in Diamond Valley on exploring the relationship between evapotranspiration and irrigation for use in water management. I'd like to thank Justin Huntington, my thesis advisor, as well as Charles Morton and Matt Bromley, and a bunch of others at DRI who assisted me during my master's work. I'd also like to mention OpenET, who provided the models to run the satellite-based evapotranspiration models, which we will talk about later. I'd also like to acknowledge Nevada Water Resources Association, as they provided many opportunities for me as a graduate student, from scholarships to networking and presenting my research through poster competitions at their conferences. Alright, without any further ado, let's get into it. So we're going to start out with a little bit of an introduction. We're going to go into the background as well as the approach that we're going to be using. Background's going to include a little bit about evapotranspiration and irrigation as well. And then we'll kind of progress into data and methods, including study site, pumping data, ET models, and pairing pumping and ET data. Then we'll go into the results of the model as well as its performance and its prediction capabilities. And we'll go into a little bit of discussion and conclusion. The photo on the right here is an interesting photo, actually. It's from my family farm back in California. This hay is from Orvada, Nevada. That's where we buy our hay. And it was just kind of an interesting thing to see kind of where the hay ends up going. All right, water use in Nevada. Many western hydrologic basins are over-appropriated, and Nevada is no exception. Of the 256 basins in Nevada, over 96 are over-appropriated. See the figure from a presentation by Jason King, the prior Nevada State engineer. We see here that Diamond Valley is highlighted in yellow and has a committed water rights above 100% of the perennial yield, as well as pumping over 100% of the perennial yield. In Nevada, 70% of the groundwater is used for irrigation. Nevada, like other western states, have put forth new groundwater policies and laws, many of which require reporting the pumping of groundwater. These new laws are in response to the over-appropriation of these basins. So these are just a few examples of groundwater policies across some western states. In California, we have SGMA, passed in 2015, which requires basins to attain equilibrium by a given date, depending on the severity of overpumping. In Kansas, we have the local enhancement management areas, which require enhanced management for specific regions, which typically involved reporting of groundwater use. Here in Nevada, we have the critical management areas, which is a designation given by the Nevada State Engineer to basins where groundwater pumping is in excess of perennial yields. It requires the basins to develop a plan to come into balance within a given period of time. As the business saying goes, you can't manage what you don't measure. As such, many water management plans will involve mandatory reporting of groundwater pumping. Questions and concerns about the quality and validity of pumping data may become a source of conflict. Therefore, a complementary and independent method to assess pumping is needed. How is pumping currently estimated today besides using pumping meters, like the one shown in this figure? One of the more common methods of today to estimate pumping is through the use of evapotranspiration to calculate the net irrigation water requirement. Evapotranspiration, or ET, is the water that is needed by the plant to grow and function, in addition to water that is evaporated from the surface. This can be thought of as the opposite of precipitation. It's the water that leaves the surface instead of what comes down. Evapotranspiration is a consumptive use and is not returned to the system. So once the water evaporates, it does not come back or is no longer available in that area. The net irrigation water requirement is ET minus effective precipitation. Since irrigated crops in Nevada and many other places across the West require more water than what is provided by precipitation, additional water is needed for the crop to grow. Essentially, how much water in addition to what is provided by the environment must the farmer add in order to achieve a healthy crop? That is the net irrigation water requirement. So, in Diamond Valley, we have a net irrigation water requirement of 762 millimeters per year, or 2.5 feet per year. Multiplied by a typical pivot size of 50 hectares, we get 386,000 cubic meters of water use per year, or 313 acre-feet per year. But what about losses? Some of the irrigated water is lost to wind drift and deep percolation, and is not made available to the plant. A typical pivot is about 85% efficient, meaning 85% of water being applied is actually used by the plant for ET. So, we divide our previous figure by 0.85 and get 450,000 cubic meters per year, or 367 acre-feet per year. However, this assumes the crop is well watered and grown to its full potentials, which is not the case. Disease, different farming practices, and soil conditions can cause deviations from this ideal amount. This is where remote sensing comes in. Satellites can capture the spatial and temporal variability in crop conditions, utilizing multiple images taken throughout the year. This figure shows Ndvi, or the Normalized Difference Vegetation Index, which is a measure of vegetation vigor at the surface. In many of the fields, there is a large amount of variability, which is not accounted for by the net irrigation water requirement. So we can see here that some of these fields are there's half of it that's being irrigated, half of it might not be. This one has some strange stripes going on with it, and there's just a whole lot of variability in each field, which is not accounted for in the current estimates of evapotranspiration, particularly through the net irrigation water requirement. So, our approach is to employ several well-established satellite-based ET models to estimate field-scale evapotranspiration. We want to pair modeled ET with reported pumpage derived from meter data. Then develop a regression model to predict pumping based on ET. And then we want to assess this model's accuracy by cross-validation, as well as assess the model performance across the basin and compare with estimates made by other methods. The study area. Our study area is, as you could have guessed, Diamond Valley, which is located in central Nevada, and home to 26,000 acres of irrigated farmland, almost exclusively on groundwater. Recharge is estimated at 35,000 acre-feet per year, while pumping is estimated at 76,000 acre-feet per year. Thus, it was designated a critical management area in 2015, which begun the Groundwater Management Plan. Currently, the Groundwater Management Plan is in litigation. However, in addition to the critical management area designation, the Nevada State Engineer also passed Order 1251, requiring the reporting of pumped groundwater on a monthly basis in Diamond Valley. This is the main reason why Diamond Valley was chosen as the study site, as we have a large amount of high-quality pumping data available. The main irrigation system in Diamond Valley is pivot irrigation. In these figures, we see pivots are composed of irrigation lines suspended over the field, which rotate around a center, providing water to the crop, hence their circles. Along the main line, there are hoses that come down to individual sprayers. There are a very large diversity in systems in Diamond Valley with varying sprinkler heights and types. Down here we see a few of these. We have an IWAP here, which sprays out larger droplets to a larger area. This is a similar one here, except it's running. And then we have a sprayer type here, which is more of just a flat spray. So now for a little size context. It is a bit hard to get a grasp for how large these pivots are. They're about a half a mile in diameter, which is enough to cover the entire UNR campus with only 2 pivots, as well as Levi Stadium, in addition to the parking lot. So these are quite large pivots, and they use quite a bit of water. Flow meters in Diamond Valley are composed of meters from the Idaho Department of Water Resources list of approved closed conduit flow meters. Most farmers installed SIMS-MAG 5100Ws, which can be seen in the yellow ovals on the pictures to the right. Data is available for 2018 and 2019, but the challenge is figuring out where the water from each well is being applied without any overlaps. This sounds like a simple task, but it definitely wasn't. So a little bit about water rights in Nevada. Each water right has both a point of diversion, which can be a well or a ditch. It's essentially where the water is being diverted from its main source, as well as a place of use. This is where, this is the maximum extent to which the water can be applied. Then there is the actual irrigated area where the water is being applied. Simple enough. However, multiple water rights can be applied for a single well, resulting in multiple places of use for a given diversion. Also, the places of use can overlap with different water rights, making things much more complicated. Here we have 3 fields in Diamond Valley. This is one place of use, and another, all intersecting each other. The actual location of the point of diversion is not as critical, since the place of use is where the water is actually being applied. We could have a well a good distance away from the center of the pivot and even outside of the place of use, and there could be irrigation lines subsurface or surface providing water to that pivot. The intersect of the polygons is drawn and is called the area of intersection. No other place of use intersects these 3 fields. Now we can take the pumping from the points of diversion associated with the places of use, X, Y, and Z, and link the total to the ET from fields 1, 2, and 3. And we get something like this. We have a list of area of intersection IDs and the application numbers, which is the place of use ID, which are encompassed inside of that area of intersection. We also have a list of field IDs, which are also inside of that area of intersection. This way, we can get the pumping amounts from these application numbers or places of use and link them to the evapotranspiration found over the actual field areas. In some cases we have 1-to-1, but in many cases it's much more than that. In this case we have 5 application numbers associated with a single field, or sorry, 2 field IDs. Typically, evapotranspiration estimates are made using a combination of weather station-based reference evapotranspiration and predefined crop coefficient values. The reference ET can be thought of as a theoretical rate that is dependent on climate conditions and a theoretical grass surface. It is calculated using solar radiation, relative humidity, wind speed, and temperature. However, it is the evapotranspiration for this grass condition. To scale it to another crop, such as alfalfa, the crop coefficient is used. The crop coefficient can vary depending on crop phenology. In the case of alfalfa, we see it begins green up around mid-April and then oscillates for the rest of the season due to cuttings, that we see here. Once the reference ET and crop coefficient are multiplied, actual evapotranspiration for the specific crop is achieved. There are a number of different crop coefficients ranging from alfalfa to corn to trees to soybeans, tomatoes, all sorts of stuff. However, is this actual evapotranspiration? Heterogeneity in field conditions causes actual evapotranspiration to deviate from these ideal conditions. Also, soil quality, farming practices such as cut timings, and a host of other things can cause actual evapotranspiration to be less than predicted using this method. As we can see here on the left, we have a very nice homogeneous field. There are a few stripings due to the wheels of the pivot going around, but for the most part it is very even. On the right, we have another field that is much less even. There's a fairly large difference between the amount of vegetation at the surface. This can lead to fairly significant changes in actual evapotranspiration. With remote sensing, things are done a little differently. Instead of using a single weather station, gridded climate products are used to calculate reference ET. Instead of using predefined crop coefficient values, they are calculated using satellite imagery, which encompasses the spatial and temporal variability of the field. Combined, these give us actual evapotranspiration. GridMet is a gridded climate dataset for the continuous United States. It has a 4-kilometer resolution and has a daily timescale. So on any given day and location, we can estimate daily reference ET as opposed to a single point estimate from a weather station. So, the fraction of reference ET is calculated using satellite imagery. There are two main approaches. The first uses land surface temperature to solve the surface energy balance for the latent heat flux component, this term here. Here, cold pixels experience higher ET since more of the incoming energy is going towards evaporating water and not heating up the land surface. As can be seen in the figure on the left, the land surface temperature over irrigated pivots where lots of ET is occurring, the temperature is 80 degrees, while over the native sagebrush vegetation in the surrounding area, little ET is occurring and the surface temperature is much hotter at 135 degrees Fahrenheit. The other method uses vegetation index, known as Normalized Difference Vegetation Index, or Ndvi. The index varies between -1 and 1, where higher numbers indicate more vegetation and thus a higher fraction of ET. We can see here that the surrounding sagebrush area has a very low Ndvi and is also evapotranspiring at a much lower rate than the pivots are, where it's much greener and there is much higher Ndvi values. The three satellite-based ET models we'll be using are Metric, CBOP, and SIMS. Metric stands for Mapping Evapotranspiration at High Resolution with Internalized Calibration. CBOP stands for Simplified Surface Energy Balance Model Parameterized for Operational Applications. Metric and CBOP utilize the surface energy balance approach using land surface temperature. SIMS stands for Satellite Irrigation Management Support and utilizes the Vegetation Index approach. Below is the new method. Here we have a time series of reference ET. As we expect, it goes up in the summer as there is more available energy and higher temperatures to facilitate ET. In the middle is our customized on a pixel level fraction of reference ET, or crop coefficient time series. Multiplied together, we get a time series of actual ET which can be integrated in order to achieve ET for any given period. These models were run in Google Earth Engine as part of the OpenET project. The goal of OpenET is to provide easily accessible satellite-based estimates of evapotranspiration. As we can see here, there are delineated actual irrigated areas which can be selected, and the time series of evapotranspiration can be displayed. OpenET is still under development. However, I was able to gain have access to some of the preliminary data using previously mentioned models. As mentioned, this uses Google Earth Engine, which is a cloud computing. So all the remote sensing data is stored on the cloud, and the algorithms and the models are brought to the data instead of the other way around, making it a much more efficient system and easily scalable. To assess model performance of the satellite-based models, we compared modeled ETF with mean Ndvi for both 2018 and 2019, where we had available pumping data. Ndvi and ETF should have an approximate linear relationship that is consistent from year to year. In the figure to the left, we see that there is a consistent linear relationship from year to year without any significant outliers. This one is a little bit out there, but it is within the Pearson coefficient of 2, thus it was not removed. This is a good sign that the models are performing as expected. We also compared net ET for each field to the net irrigation water requirement for Diamond Valley in 2018 and 2019. In 2018, the net irrigation water requirement was about 800 millimeters and 700 millimeters in 2019, a little bit less. As mentioned before, this is seen as an upper bound since it assumes ideal conditions. In both years, the models have a value less than the net irrigation water requirement, with many values falling considerably less than the ideal conditions, showing how far a field can be from these ideal conditions and the importance of using remote sensing to estimate this fraction of reference ET. We saw previously that 2019 had a much lower net irrigation water requirement. This is a result of the increased precipitation for 2019 over 2018. Since the net irrigation water requirement is evapotranspiration minus effective precipitation, this causes a lower net irrigation water requirement for 2019. So we can see here from the 30-year average, 2018 had a bit below average, while 2019 had a bit above average. So that's what caused such a stark difference between the two net irrigation water requirements for those years. Here we see a graph of our net ET in millimeters per year against our pumping depth in millimeters per year as well. This value here is the one-to-one line, and the circled values are outliers. In order to identify these outliers, we ran a Pearson coefficient test with bounds 2 and -2. These outliers were investigated to find possible sources of error. The high outliers up here were found to most likely be a result of irrigating outside of the place of use. This would cause the pumping for that well to be high because it wasn't accounted for since we were only looking at ET from within the place of use. The low outliers were likely caused by erroneous pumping data, reporting errors, or spatially join errors causing no pumping data to be linked with the ET values. This only occurred a few times on these 0 locations here, since no pumping data was linked to the ET value. However, these other locations here were investigated, and this was the reported pumping data that they had. We can see based on the ET that these are very low, likely a report error or a measurement error from the meter. The calculated pumping values on these yellow diamonds are fields where pumping data was not reported. The Nevada Department of Water Resources then used the net irrigation water requirement divided by the efficiency, or 0.85, multiplied by the area of irrigation in order to estimate pumping for those fields. Since these were not a direct measure, they were excluded from the regression. We can also see that they tend to be much higher than the rest of the pumping values, kind of indicating the importance of using this evapotranspiration method to estimate pumping. And this is it, the final regression with confidence and prediction intervals. The efficiency is calculated to be approximately 80%, which is quite close to the assumed 85% of most pivots. The excessively sandy soil in the basin may lead to the lower overall efficiency, calculated using this method. The R squared is approximately 0.65, which is quite low, but not surprising due to the large variability in system types, farming practices, as well as soil types in Diamond Valley. The prediction band equation is shown here by the formula of the linear regression plus or minus the prediction interval, which is dependent on the net ET as well. For example, if we were to have a AT value of approximately 600, we would use the linear regression to get here, which has probably about 725 or so millimeters of pumping, plus or minus the value shown here. We used a threefold cross-validation approach to evaluate the model, which resulted in a mean absolute error of 93.6 millimeters and a mean absolute error of 18%, which is not bad considering the amount of variability in the system. This graph compares our predicted pumping to other methods and the reported pumping by Nevada Department of Water Resources over the entire basin, shown in black. We see that our model prediction is quite close to the reported Nevada Department of Water Resources pumping value for both 2018 and 2019. We also see that the other methods tend to overestimate pumping by a fairly large margin. These methods utilize the net irrigation water requirement divided by some efficiency approach mentioned previously, thus not accounting for any deviations from these ideal conditions. Essentially, it's assuming that every field is evapotranspiring at the ideal conditions, thus requiring the ideal amount of groundwater pumping, which, as we saw from the histograms and the scattering in the regression plots, does not seem to be the case. We suspect that this is why our estimate is lower than the Nevada Department of Water Resources, since they used some degree of net irrigation water requirement divided by that 0.85 in order to gap fill where pumping data was not reported.
So what can this model be used for? One of the more important uses is of identifying erroneous pumping data. Data points falling outside of the confidence interval could be further investigated for error. If the error is related to meter failure, then points will consistently plot outside of the prediction interval from year to year. However, only 2 years of data are available. As more data comes in, the more robust this model will be, as well as our ability to identify erroneous meters. This model could also be used in other basins. However, since they are different systems, i.e. they have different pivots, they have different sprinklers, they have different irrigation methods, some of them may be more flood irrigated, this model may require some adjustment. Diamond Valley's diversity in irrigation system, type, and soils might allow it to be used in other basins without too much adjustment, but that still has to be investigated. Currently, we're actually looking in Harney Basin to see how well this model translates up there, as well as developing an independent model in the Harney Basin using pumping data from there. So we'll see where this one goes, but this is an interesting point. It also has the potential to estimate historical pumping, since Landsat imagery used in the satellite-based models go back all the way to 1984. That's almost 40 years now. However, current irrigation systems are different from historical systems, and since the ET models don't see this difference in efficiency, they're only looking at the actual evapotranspiration, the slope of this graph may need to be adjusted in order to account for these historical differences. However, the spread or the diversity in systems shown in the graph will be an important part in predicting a confidence interval going back in time, or sorry, a prediction interval going back in time. So, for some final thoughts, remote sensing ET estimates can be a powerful tool for water resources management. They provide a second check when assessing field and basin scale pumping data. They identify outliers and potential areas for improved water use efficiency. However, it is also important to provide communication with farmers as to the nature of the data, as the idea of having an eye in the sky can be very dangerous in terms of trust between the farmer and the water manager. So it's important to communicate what data is being used to assess water in their areas. Future work is needed in assessing if this regression model is valid for other years and other basins, as this has a very powerful capability of looking at water use in other basins. It's important for us to understand how it can be translated to those other areas, as well as historically. And these are my citations. And do we have any questions? Thank you very much for coming to my presentation.